Okay, so thank you for the kind introduction, and thanks for having me. My name is Gábor Szárnyas. I work at DuckDB Labs as a developer relations advocate, and I'm here to talk about DuckDB, which brings the power of a data warehouse in your Python process. So first, a very brief introduction. I come from academia. I studied in Hungary and did a PhD in software engineering in the Technical University of Budapest. And I slowly drifted towards data-driven topics, data engineering, and building data processing systems. So in 2020, I moved to the Netherlands, and I moved to an institute called CWI, which does research on database systems. Maybe CWI is not very well known outside of Europe. It is actually the birthplace of Python, so it's a very nice connection to this event. Python was created there in 1989. I was part of the database group, and the database group was the one which created this system called DuckDB, which I will talk about today. So DuckDB is now backed by a company called DuckDB Labs, which is also located in Amsterdam. We are a small startup of about 15, 16 people, and we work on the development of DuckDB, and we provide commercial support services for DuckDB. So just to get an idea of your familiarity here, who here has heard about DuckDB before? That is 1, 2 hands, and who has used DuckDB before? That's 0 hands. Okay, so I think I can tell you some information about this system. So the context of this is the field of data science, which is a relatively new field and has been very popular in the last 10 to 15 years or so. This figure shows what is called a data science workflow, which starts by asking an interesting question. You have a problem domain, and you want to answer some sort of an interesting question that you think will help your business or it will help your research. Once you have this question, of course, you need some data to back it up. That's why it's called data science. So data comes in all shapes of forms. You have CSV files, Parquet files, JSON files. You often have binary formats, and you get these data sets, you load them in a system, explore them, and then once you have explored them, maybe you build some machine learning model on it, maybe you create a visualization with Matplotlib, Plotly, and so on. And this is iterative, so you keep repeating it, you pose more questions, and you try to extract more and more value from the data. And we would like to focus on the middle part, exploring the data. This is difficult to do from an integration perspective because you have all the different data formats that you need to handle. And it's also difficult because it's computationally challenging to process large amounts of data. Not to mention that once you have finished exploring the data, you need to pass it on the next layer in some format that those libraries like PyTorch, TensorFlow, and the others can consume. So there are a couple of choices for exploring data, and I think you have already used a few of these options before. The go-to option for most data scientists is to use data frame libraries. Pandas is very well known in the Python community, and Polars is also a popular new choice for working on data frames. The problem here, especially in the case of Pandas, is that it has severe performance limitations. Pandas is running on a single thread, so running queries takes a long time, loading takes a long time, and these systems don't really have query optimizers, so the data scientist is left on their own to formulate their problems in API calls that you stitch together in a lazy manner and then evaluate it once. These systems tend to run out of memory if you have quite complex problems. And when Pandas runs out of memory, that's when most data scientists switch to something like Spark or Dask, which are distributed computing systems. So here, you can run multiple computers, and you will not run out of memory, but you will have the burden of configuring that cluster, paying for that cluster, and operating that cluster. Not to mention that even if you have all this done, it indeed scales, but it has a big performance impact. And even for middle-sized data sets, it can be slower than what you would expect from a large cluster of computers. And finally, we have data warehouses, which on the surface look like the perfect choice. These are database systems that are geared towards analytics. They have very sophisticated query engines. So in principle, they would be excellent for taking data, ingesting it, and exploring it quickly. The problem is that they are also quite difficult to operate. They can be very expensive to license because most of these are proprietary systems. And it is difficult to get the data in the data warehouse and then get the data out of the data warehouse for future use, like plotting and machine learning. So we think there is room for improvement in this box of exploring data. And hence we created DuckDB. In a nutshell, DuckDB is an analytical SQL database. So it has the sophisticated architecture of a data warehouse, but it is made for data scientists to be easy to use. It has been developed since 2018. It's written entirely in C++11, and it has no external dependencies, so it is very portable. And it has been gaining popularity quite a lot. In the Python world, we have more than 1.5 million downloads a month on the PyPI repository. A question that you might naturally ask, why is it called DuckDB? Well, in Amsterdam, we have many canals, and people often live on a boat. So one of our co-founders, Hannes, lived on a boat and wanted a pet, and he picked a duck, because a duck is, of course, a very practical animal to have on a boat because it can swim and is not afraid of water at all. So this is Hannes and his pet duck, Wilbur. DuckDB was named in the honor of Wilbur. So the rest of the talk, I will talk about DuckDB's unique features and what makes it work and how does it work. Key among these is that it is an in-process database, which may need a bit of explanation. So traditionally, in the database world and in the data warehouse world, you have a client-server setup. You have the database server on the right, and you have some client application on the left. And this is often quite challenging to deal with. First, you have to set up a database. You can maybe run it in a cloud or run it on premises on a server, but you have to configure this database, you have to create users, and then you have to continuously run it or start it when it's necessary. Once you have that user, you have to authenticate. So you have to set up the client application with the correct address to the database, the correct user, and the correct password. This is all very tedious, and even if you do all this, you will be limited by this little line in the between, which is the client protocol, which makes it necessary to take the data that you have in your local process and transfer it to the remote database. Especially if you deal big data sets and you pass tables back and forth, this can be very limiting on performance. The other problem is that it's difficult to ingest data. If you have your input sources like the CSV files on your local machine, then you have to push it through the client protocol. If you have it on the server, then you have to somehow address those data files, and it's all very tedious to get the data there. So again, this is a problem. So what DuckDB does is that it rethinks this architecture and says, how about taking the database and bringing it into the client application? That's why we call it in process, because it runs in the client application process. You can see that the code shrunk by quite a lot because we no longer need to address, authenticate, or do any of that setup. We just say we connect to this database. The database is now a single file on the disk that contains all your tables and all your data, and then you can start running your queries. So it also makes it simpler to just ingest the CSV files because it's obvious that you have a single machine and you have the CSV files there and you have the application and the database all running on that machine. Of course, this in-process thing is not entirely new. If we take a look at a categorization of the database systems, you can spot that SQLite, which is a very popular embedded SQL database, is on the top left corner under in process. So why don't we use SQLite for data science? Well, the thing is that SQLite is geared towards what we call transactional workloads. Transactional workloads are heavy in writes, and they typically run queries that only touch on small portions of the data. So SQLite is an excellent choice if you need to save some configuration, if you need to just write some cookies down for your browser, etc. But it doesn't really work for data science where you have gigabytes of data frames that you have to crunch over and over again to get some information out of it. So DuckDB is currently the only system that we are aware of that sits in the top right under in process and analytical. DuckDB is a free system. This is very important because a lot of the issues with using database management systems and data warehouses is that they are expensive, and also having a license is more complicated than not having a license. It can be tricky to set up those systems and adding a license file. So DuckDB is an open source system. You can go on GitHub. It's distributed under the very permissive MIT license. So you can fork it. You can create your own version of DuckDB. You can use it internally. This is all allowed by the license. DuckDB is also free in the sense that you do not need to run a server. You do not need to pay for a cloud instance or any other things like that. DuckDB is capable of doing relatively large data processing tasks just on your laptop. It turns out that the laptops in the last 10 to 15 years have developed a lot. So most of them have more than 4 CPU cores. They have reasonably fast disks, and they have quite a lot of memory. So you can get a long way with a laptop. DuckDB is fast. This is, of course, very important if you do data science. But how can it be so fast? How come none of the other systems do this? Well, the trick is, to a large extent, in the data layout. So I mentioned that we have transactional systems which are write-heavy, and the queries typically access only a small amount of the data. For these systems, something called a row storage or row-based layout is the ideal one. This allows individual rows to be fetched very cheaply, so the system can just target a single data point and get all the attributes that that data has. So this is great for some workloads, but if we have a different workload where we are only interested in the values of a few columns, which is very typical in data science, then this is wasteful. So we have something called columnar data storage for that. That's already used by data warehouses and, of course, also DuckDB. Here, the data is stored by column on the disk, and we can fetch individual columns. So if someone asks, what if we're only interested in the price of a product, but we don't care about dates and store and the customer? Well, then we can skip scanning 60% of the data. And this leads to immense savings in terms of disk I/O and memory. Not to mention that if we store the data based on the column, we will have data that is very similar as we scan it on the disk. So if we have a date column, the date doesn't really change that much between two subsequent values of the same column. So we can use heavy compression. Let's walk through an example. Suppose we have a 1 terabyte table with 100 columns, and we have a query that only requires 5 of these columns to be evaluated. If we do a row-based representation, we have to go through the entire 1 terabyte of the data at a disk speed of 100 megabytes, which is reasonable for a fast HDD. This will take 3 hours. But if you use columnar storage, it goes down to just 50 gigabytes, which can be done in approximately 8 minutes. And this is before compression, because if we use compression, then we can save approximately 3 to 5x further size of the data. Here is actually a very nice history of how this was improved in DuckDB. So initially, DuckDB did not have compression, and then we added various compression methods like run length encoding, bit packing, dictionary, and new compression methods that the team in Amsterdam has invented. And based from no compression, we went to a 5x saving on some data, which is from the TPCH benchmark. So if we continue the example that we have done in the slide before, we can go down from roughly 8 minutes of scanning to just 1 minute and 40 seconds. So we have saved roughly 100x on scanning the data and getting it into the query engine for processing. And that is, of course, quite a significant difference. The other significant difference is the query execution method. So the SQLite system and the other systems with transactional processing use something called tuple at a time, meaning they process one row at a time. Pandas does column at a time, and DuckDB uses vectorized processing. I will explain these through examples. So in tuple at a time processing, we optimize for having low memory footprint. This is very important because these systems come from an age where memory was at a premium. So you can run very complex queries by only keeping a single row in memory and the related intermediate results. The problem is that this has a very high CPU overhead. So if you have millions of rows to go through, then you will have that overhead times 1,000,000. And in turn, your query processing will be very slow. Your CPU will be constantly forced to switch context. And this is just not efficient for data science workloads. A better approach is the column at a time approach. This is used by pandas. So it takes one column and it takes the other column and it runs them through the operators that you define. The problem here is that it takes an entire column at once. So it has to materialize large intermediate data sets in memory, and that can measure to gigabytes or larger each. And this can get you out of memory exceptions, so it will cause your system to crash if you select too large data sets. So the ideal solution is somewhere in the middle. We should strive to use some sort of a columnar processing, but limit the size and not take an entire column at once. And there are techniques for that. It's called vectorized processing. It basically means that you take a chunk of the columns and manage to put that through the query process. This allows you to have good CPU locality, and it allows you to also use something called single instruction multiple data, which are built-in instructions in modern CPUs that allow you to process multiple data items at once with a single CPU instruction. So you get a lot of built-in parallelism, even if you just run on a single thread. So this is the best approach to exploit the modern CPU architecture, which is actually quite complicated and has huge differences between latency in the CPU cache, like L1, L2, and the main memory. You can see in the example here that there is also a 100x difference here in terms of the latency for the L1 cache and the main memory. So DuckDB exploits that and tries to formulate the queries in a way that you can keep them in the L1 cache. Of course, this is very challenging to port between different computer architectures because different computer architectures have slightly different CPU instructions. More on that later. Finally, one strong point of DuckDB is that it has all the bells and whistles of a data warehouse. It can take expressions in queries and rewrite them to more efficient forms. It can reorder the joins in the queries. It can flatten subqueries, and it can do filter and projection pushdowns. These are things that pandas can also do, but this is automatic in DuckDB and manual in pandas. So we can run queries quickly, we can store the data quickly, but can we load the data quickly? Well, thankfully, DuckDB has a highly optimized parallel CSV loader, and we believe this is very important because data science is ultimately an interactive sort of genre. You sit in front of the computer and you don't want to grab another coffee every time you load a new data set. So I prepared a little demo with a synthetic social network benchmark data set, which is available online. So let's see how this works. We have a directory called person. So this is the social network and the people in the network. If we read into the file, we can see that it's called a CSV file, but it's not actually comma separated. It has pipes as the separators, and it has fields that you would expect from a social network. People have names and genders and birthdays and email addresses. So we can roughly see that each line in the CSV file corresponds to an individual person in the network. So let's see how this looks like if we want to get this to pandas. So I will first run this query and then explain what it does. So here we take the person directory and go through the CSV files. We explain pandas that there is a pipe separator in the file, and then we concatenate all these files after each other, and we get the final data frame that encodes the persons in the network. And now that I talked this through, 17.5 seconds passed, and pandas loaded all the data frames concatenated them together, and it says that there are 8.9 million people in this network. So this is rather slow. You would be tempted to check your email or write some messages. So maybe Spark will be faster. Let's see. So I will again run this. Spark has started. We also explained to Spark that the files have headers. We use the pipe as the delimiter, and it has to load it from the person directory. And it's loading, and it's 11.7 seconds. So it's slightly faster than pandas because it can run on multiple CPU cores, so it can parallelize, but it's still rather slow. Let's see DuckDB. So we have this magic DuckDB loaded, and we can run this simple expression on DuckDB that creates a table called person from the CSV files. Note that we didn't specify that it has to be a pipe separator. DuckDB will try to figure it on its own. And DuckDB takes roughly 1.6 seconds. So more than 10 times faster than pandas, and about 6 times faster than what Spark was. And you can see that it did all the work because it has the same number, 8.9 million people in the network. And now that we have it here, we can run queries on it. So this is, as I said, roughly 9 million people, and you can run queries like selecting the people who have a birthday, and it is kind of snappy. It's coming back to you interactively. You can ask questions about the data, and it will run reasonably quickly, and you can browse it in the familiar Jupyter environment of Python. Okay, so this was the loader part of the demo. Let's continue with the rest of the talk. As I said, we have this fast CSV loader, and it doesn't only work on the social network person dataset. I ran a more comprehensive benchmark, and on this MacBook, which I'm using for presenting, I managed to load CSV files up to 253 gigabytes. And the best thing about this is that it doesn't take a long time. So it loads that in less than 4 minutes, which amounts to more than 1 gigabyte of CSV read from the disk, parsed, turned into data tables, and then written into DuckDB's internal format. So this is all very snappy for getting started. Once we get started, we may want to get more data and run some queries. Well, DuckDB doesn't only support CSVs. It supports all the important formats that are popular in data science. So it supports the Apache Parquet format. It supports JSON files, compressed versions of these files, Iceberg, and NDJSON. And it has its own format, which is the .duckdb file that we use to persist on disk. It's very important that often the data doesn't live on your laptop. So DuckDB can read from HTTP. It can read from Amazon S3 buckets, Google Cloud, and it can also hook up to a Postgres database and just use the tables there, or a SQLite database for that matter. It's really quite flexible in terms of the data sources that it accepts. And once the data is in, we can use the powerful SQL query language. Of course, SQL is very popular in the database world, and we selected a dialect of SQL that we believe is one of the most reasonable ones. This is the PostgreSQL dialect that is supported by the PostgreSQL database and many tools that are available. We support the full dialect, including aggregations, joins, window functions, common table expressions. So it's not just the core of SQL, but also quite a few of the more sophisticated SQL features. And we think that SQL is a great language for doing analytics, but there is some room for improvement there. And I would like to highlight in particular 3 of these. So going back to the demo, we have this person table in. The table is still here. We can see that we have just 5 people selected that you can observe. But how about running a query which takes the most popular persons, the most popular first names, and lists us the 5 most popular first names? What I would write as a SQL practitioner is I would say, I'm interested in the first name, and I'm interested in how popular that is. So that would be a count aggregation. I name it as CNT for count, and then I would like to say it is something that should be ordered by the count descending, and then run the query. And something I always forget is to add the aggregation. So SQL is always complaining that if you do something like count star, you have to say group by, correct. So we can add this group by, and then SQL will be happy, and it will give us back the most popular first name, which is John, and the second one is A dot in this network. The problem is that this is something the machine could figure it out, and you're prone to forgetting it. So if you would say last name, then you would have the same issue, and then you would have to come here. So something we added in DuckDB was group by all, which says, well, take all of the attributes that are here that are not part of the aggregation, and then you can just run this and very simply include all of these columns in the aggregation. So this is something that people really appreciate, it turns out, and other SQL vendors have already copied this from DuckDB. This is one of the peak DuckDB features that we have. Another feature that we have is that you often start a query with select star, and it turns out that this is not really necessary. You can just say from person, and select star will be added automatically by the system. So, of course, sometimes you do want to select many of the attributes, but maybe here we would just like to have everything except the creation date and the email address of the people. In a traditional SQL system, you would just copy out the attribute names, and then you would start to enumerate ID, first name, etc. But in DuckDB, you can use the exclude keyword, and you can say, I want everything except the creation date and the email address of the people. And this works very nicely. You can see that now the table basically fits a single screen. If I zoom out a bit, it just removed those two attributes and kept the rest in the list. DuckDB is also neat for working with nested data. So this email attribute that I have just removed is something that is semicolon separated within the CSV file. You can see that it has this semicolon because a single person can have multiple email addresses. Well, we would like to sometimes take this apart and analyze it, and this is totally possible. We can use something called split for splitting the email address, like so. Then we have a list, and if we want to unnest that list, we can use the unnest function, and then we can see that this person has 5 email addresses, and this is already a lot easier to work with in subsequent queries. So we try to make it easy to also work with nested data in SQL. A final thing that I think is really great, and this is by no means a DuckDB invention, but this is something that DuckDB adopted from other systems, is pivot and unpivot. It turns out that in many cases, you have data like this. This is the population of big cities given in thousands of people. And you have decades of 2000, 2010, and 2020. And it is sometimes beneficial to turn this into columns. So you take the years and turn them into columns. There is an operation for this called pivot. This is already supported in Microsoft Excel and other products, but people very rarely actually use these. Well, DuckDB has this, and you can see that it is very simple syntactically. You just say pivot cities on the year using the sum of population, and then it does the pivoting. Also, you can unpivot, so you can change between this long table representation and wide table representation just by running pivot and unpivot. Okay, so we are at a PyData meetup, so let's talk about Python. But first, we would like to express our love for Python. DuckDB loves Python. We claim that Python is our primary API, and indeed, we do our utmost to support all the important features in our Python client. Part of this integration is that we want to make it easy to gradually integrate with DuckDB. And to this end, DuckDB can read pandas data frames. So DuckDB understands the binary format of the pandas data frames. Because it runs in process, in the Python process, it can actually see that area of the memory. So if you have something like my_df in this example, then you can just write your DuckDB SQL queries saying, I want to select the average of this value from my_df, and it will give you back a DuckDB table that has the correct answer, 42.5. What's more, you can then take this answer and turn it back into a pandas data frame by just saying .df parentheses, and then you're back in pandas land. So this is all very easy and seamless, and unlike with most approaches that we have seen, here you do not have to create a copy. So this is called a zero-copy access. DuckDB just sees the pandas data frame in the memory and operates directly on that without doing any extra unnecessary steps. We can also work with NumPy arrays. NumPy is, of course, very popular in Python, and it's processed by many of the machine learning libraries. You can take a pandas data frame, query it from DuckDB, and then fetch it using the fetch NumPy function, which will give you back a dictionary of NumPy arrays. And then you can take the dictionary, fetch a value from it, like my array A has this array of 42 and 43, and then you can use NumPy np.sum to work on it. So this is, again, for improved integration with existing Python libraries. We understand that not all of the people use Python, so DuckDB is very portable. In fact, we have a command line client that you can run in the shell. On the Python end, we have, of course, pip install, but we also have an R package, and we support more than 10 other languages. We have a Java client, a Julia client, a Rust client, and so on. So DuckDB is really very portable for all of these languages. And this is actually more tricky than it seems on the first place, because nowadays we have quite a heterogeneous landscape of operating systems and architectures. We have Linux, which is absolutely dominating in the server world. We have Windows, which is quite dominating in the business world still. And we have macOS, which is popular for desktop computers. And we have different architectures, x86 from Intel and AMD. And we have ARM running on the Macintosh computers, in the Amazon cloud, and all the smartphones, and some Microsoft computers as well. So this can be quite tricky, especially if we multiply it with all the languages. Then it is sometimes daunting, because if you take this laptop, and the demo I have just shown, that was Python, Apple, and ARM. But if we talk to a data scientist that works on Windows, that may be R, Windows, and x86. So having support for all of these combinations is quite a large effort, and we do our best to ship all the precompiled binary packages so that people can indeed do pip install or install those packages in R and just work it immediately on their computers. So DuckDB on its own is already quite a powerful system, but there is always room for adding more extensions, because there are so many formats and so many possible integrations that we have an extension mechanism. This allows you to define types, define your user-defined functions, define more syntax elements for DuckDB, new file formats, new compression methods, and so on. And in fact, many of the important features that I have shown are already implemented as extensions in main DuckDB. We have quite a few popular extensions: full text search for working with natural text, and geospatial for working with geospatial data. I have one example for geospatial here. This adds types which allow you to model maps by defining points and polygons, and it has functions like calculating distances. And once you have this, it adds all these user-defined functions to your SQL, and you can do things like calculating the aerial distance between 2 points trivially in something like the New York taxi data set. So this seems good, but what is DuckDB actually used for? And the answer may be a bit surprising. One of the peak use cases of DuckDB is just saving costs. So people, of course, want to save the cost of their development time, and they want to save the cost of them just waiting and stirring their coffee until the query finishes. And they also want to save the cost of running a Spark cluster or working with a cloud data warehouse. So when the talk title says the power of a data warehouse in your Python process, this is something that we mean, and this is something that can benefit in significant time and cost savings. And this deep integration that we have with Python and that I talked about is something that allows you to take an existing Python script and optimize it gradually. So we don't expect you to buy into DuckDB and rewrite everything in the form of DuckDB tables and DuckDB SQL queries. If only a single part of your Python script is slow, you're very welcome to try and use DuckDB to take that particular part and try to run it faster. Maybe you will just use DuckDB for loading the CSVs, or maybe you will just use it for a single complicated join operation. It is completely up to you. One particular use case that is unique to DuckDB and I would like to mention is that it runs through WebAssembly in browsers. So you can go to shell.duckdb.org, and this will run in browser. So this may need a bit of explanation because we already did the Jupyter example, but with the Jupyter example, the queries are typed in the browser but run in a Python process on the background. Here, the entire thing runs in the browser. You can take a phone, you can run DuckDB on it and use the shell, and it will run within the phone's integrated browser. So this is something that is thanks to DuckDB's extreme portability. And of course, we don't expect many end users to open a browser and do complicated number crunching in it, but it's very useful for something that's called a last mile analytics, which is you have some data somewhere and you have processed it down to the last 100 lines, and then you would like to visualize it. But in the visualization, you have some filtering, you have some sorting, etc. Here, you can use DuckDB to take that and run the final processing step before you visualize it for the user. And this results in a very snappy user experience where you have a dashboard that responds immediately to your filtering, ordering, and other operations. So DuckDB is, of course, an open source software project, but there are a few organizations around it, and people sometimes ask us what all these are about. Well, DuckDB is a project that is under something called the DuckDB Foundation. The foundation owns the project's intellectual property rights and allows people to use it under the MIT license. There is a company where I also work, which is called DuckDB Labs. This is the company that does most of the development and provides commercial support services for DuckDB. And there is an American startup called MotherDuck. MotherDuck provides a serverless platform that runs on DuckDB, and it implements something called hybrid query execution, where you have your DuckDB in your laptop, but also you have MotherDuck running on a server, which can potentially run part of a complicated query. This is called hybrid query execution, and it's a novel approach to running queries in a cloud data warehouse and a local system in a hybrid shared fashion. So if you found this interesting, then please give DuckDB a spin. If you don't really want to install anything, you can even go to Google Collaboratory. DuckDB is pre-installed, so you can just start a new Google Colab notebook, say import DuckDB, and get started with it. It's very easy, and especially students, we found, like working with this very much because of the ease of the setup. We have a comprehensive documentation. We have both a detailed reference for all our functions and types and syntax, and we have guides on how one should use DuckDB. It's now spanning more than 800 pages, so we hope that whatever you're looking for is in the docs. If not, just please reach out. So to sum up, DuckDB is an in-process analytical data management system. It is portable, it is feature-rich, it's fast, and it supports a wide array of languages. But Python has a special place in our hearts. So if you're here, you will likely approach DuckDB from Python. We have an active online community, so if you would like to stay in touch, join our Discord, follow us on X, and just visit our website. So thank you very much, and don't forget to take some of our swag. So we have baseball caps and stickers as merchandise for you. Thank you for being very attentive. Thank you. So we have time for Q&A. Let's start with the first row.
So thanks for the presentation. It's a really interesting project. And it is something similar, I mean, in SQL part with Snowflake, because the Snowflake has the many features that you describe. So my question is related to SQL part. So what about the constraint, like the primary keys on the other constraint? Do it support it, and how it works? Do it make some automatic keys in some columns, like in Snowflake?
That's an excellent question, and I even have a slide for this, I think. So one of the things that people get really surprised when using DuckDB is that you barely ever use any constraints. We support primary keys and we support foreign keys, but what they actually do is they tend to make a workload slower. And the reason for that is that during the loading, you have to, of course, check whether those constraints are being adhered to by your data. And during the queries, DuckDB does not really use any of those constraints. What DuckDB has, and that is built in and happens automatically, is something called zone maps, which for each of the block on the disk store the minimum and the maximum value. And it turns out that for queries where you look up a single ID, that's usually sufficient. For queries where you scan some sort of range, that's usually a big benefit and also sufficient. So this is counterintuitive, but indexes are not really used by DuckDB. We have something called art indexes, because in some corner cases, it is indeed beneficial to have primary keys, foreign key constraints, and unique constraints. And then you can have art indexes, but only a few % of our workloads with high selectivity queries use that.
Thank you. And one more question, please. I really like the feature with when you just can select from the pandas variable. So my question is, what about performance? Why I should use DuckDB instead of pandas in that case? Because I thought if you select from the pandas data structure, the pandas should select it more efficient, because it is the data structure they are created. Yes. So how you handle this into why your approach is better?
So the main benefit that DuckDB gets is parallelism. So this laptop has 10 CPU cores at its disposal. So even if we do the same thing as pandas, which is running on a single thread, we are approximately 10 times faster if we have enough data to parallelize on. So it is mostly boiling down to parallelism. And then if you have subsequent joins, aggregations, and other operations, then the vectorized query execution model that I have shown is also faster than what pandas does, and it doesn't run at the risk of running out of memory, which can happen with pandas.
So the global interpreter lock is
the global interpreter lock doesn't affect DuckDB because its queries are run in C++. And we actually have some further improvements on that. So we have a blog post scheduled on how to work around the global interpreter lock on macOS. That was something that was implemented by ICE Hannes. And in general, we are very much looking forward to the global interpreter lock being dropped from the next Python version. So that's something that will, of course, help the user-defined functions run faster in Python. Next question.
Okay, seems like I got the mic. Thanks for the talk. Just wanted to ask, what's the price to pay?
What's
Is
the price
it that
to pay?
I have to use SQL and then until I learn your nice syntax, I have to stick to Postgres?
No, I have many answers for this. So let's confess some of the negatives. If you use DuckDB on your laptop, you will not be able to collaboratively work on the same data set. A cloud data warehouse is great if you have 1,000 data scientists working on the same data set. Then it makes sense to run it in the cloud. If you have 1,000 data scientists, then you probably also have very deep pockets to pay for that cloud data warehouse. The price to pay is also that if you have really update-heavy workloads, if your data changes frequently, then I would not really use DuckDB, especially if you have lots of deletes, then it's better if it resides in a transactional system. But we have thought about people who want to gradually move away from other systems. We have a new prototype called DuckSpark, and DuckSpark is something that allows you to use the familiar Spark interface. So DuckSpark is a drop-in replacement for Spark that implements the PySpark API. It's currently experimental, but you can already see that you build a pandas data frame, you turn it into a Spark data frame, and you extend it with a column. So this seems very much like Spark, except if you peek up, this is actually a DuckDB package that provides something called Spark sessions. So this is DuckDB running under the hood, but you can access it through the familiar Spark calls. And we also have something called the DuckDB relational API. The relational API is very similar to the pandas API. So you can run operations like aggregate, accept, filter, condition, etc. So this is probably closer to how most data scientists think about data than SQL. So you don't have to embrace the entire PostgreSQL dialect and the SQL way of thinking, which we acknowledge can be a big blocker. Question in the back?
Thank you for the interesting presentation. Two questions. First one about the support of concept of a stage, where you can ideally load many multiple and homogeneous files into a temporary structure that should be then, I don't know, loaded, like similar to Snowflake stage. And with its own file format and flexibility. Does DuckDB support, or do you have plans for adding support, like similar to its flexibility, similar to Snowflake's flexibility?
So what is the stage that you mentioned?
Stage is like a place where you can load many files from a bucket with a prefix, with particular file formats, etc., and then you can proceed with loading from there. Like imagine 100 files or whatever, more than that. Homogeneous, so the same structure. Loading all of them into a single file with a single operation and proceeding from that table, if that makes sense. So Snowflake has the idea of stage.
Right. So all of the DuckDB load operators that we use, the CSV loader, the Parquet loader, the JSON loader, support the asterisk for Joker, so you can tackle multiple files at once. I use this to load thousands of CSV files with a single instruction. If that's homogeneous, that is helpful. You can, of course, build your Python script around this and tackle different data formats and different sources one after another. And we have something called a Hive partition data source, which may be interesting for this answer. So often the data is already partitioned based on some sort of a system like the date, where the directory structure encodes the year and the month. And we also support that. Okay, next question, because you had two. I think you said two questions.
Yeah, one more, I guess.
Yes, go ahead.
In the unpivot section, I noticed do you have to explicitly mention column names in the unpivoting operation? Or can you get away with mentioning some kind of I don't know, indexing the columns, etc.? Because that's a pain sometimes if you have too many columns.
That's a very good question. And it is something that surprisingly bodes really well with the exclude syntax. Yes, you can combine them, and it makes perfect sense to do so. So I believe this is even mentioned in our documentation. So indeed, you do not have to spell out every single column. You just say you want all the columns to be unpivoted on except on the ones that you would like to keep as sort of the key. And then DuckDB does the rest for you automatically. Indeed, so we don't want to make you do work that the computer can do it for you. So this is what we call the hassle-free philosophy of DuckDB. But yeah, very nice question. All right, more questions. Yeah?
Your presentation, suppose you have 1 terabyte or 5 terabyte of data. So how DuckDB handles this challenge? Could you compare it with cloud data warehouses? And don't you think it is a little bit tricky to compare when we have a large scale? Yeah.
Yeah. So I had a slide that I just removed before this talk, and it was kind of a bonus round on the CSV loader performance. So this MacBook has a 1 terabyte disk. So it was not enough, but I took another MacBook and I ran this experiment on it. This was 2.6 terabytes of CSV file, and it took about 45 minutes to load, and it resulted in a 600 gigabytes disk file in DuckDB's native format. I think very few people have actually this amount of data. There is a point where indeed you start running out of resources with DuckDB. If you have 5 to 10 terabytes of data, I would first try MotherDuck. That does a really nice job in complementing DuckDB. And if you have maybe 100 terabytes of data, then it's definitely something where it makes perfect sense to use Spark or to use Snowflake or these cloud data warehouses. So they definitely have their use case. But if you just have up to a few hundred gigabytes, then DuckDB is perfect for you. All right.
More questions?
Yeah.
Yeah, that's again me. Just wanted to ask, so let's say I took the data, loaded, did my magic, and then if I want to, and it wasn't small, then do I export to something raw, give someone else to load again, or is there an option to keep it loaded somewhere?
It is, and it is this .db file or .duckdb. So it's a single format that contains all the tables, and this is portable between different architectures and different languages. So if I create this file on the MacBook and send it to someone with Windows and R, they will be able to read the same file. And we are currently working on finalizing this format, so it will be readable with backwards compatible releases of DuckDB in the next decade, hopefully. So that's something we would like to achieve. And the other thing that people really like to use is just to say export database, and that will give you a bunch of Parquet files. And that's great because that's a very widely ingested format. Then you can take it into Spark, take it into Snowflake and other systems. So indeed, after a lengthy ingestion process, it makes sense to keep a more portable binary format like Parquet or DuckDB's own format. Okay, maybe one last question from the front row.
one question regarding supporting of arrays columns.
Yeah.
Because in my previous company there were a problem like we are storing in column feature vectors of person, for example, and searching through this array in standard SQL database, it was really hard and painful. Yep. What about your database? Is it fast looking through the array elements, I mean?
Yes. So we have realized that vector databases are now a big thing, thanks to machine learning, natural language processing, and other AI solutions. And we are working very hard to give something called a fixed length list support, and that will improve the performance when you are looking for vectors or you're running operations on vectors. So this is something that is already in DuckDB, but it's not in its final form yet. It will be faster in the near future. Cool.
Thank you.
Yeah, thank you so much.